Chapter 12, Solutions. First, we're going to talk about water. Water is everywhere around us. It's interesting to think that 78% of our bodies by mass contain water. Our brains are 70% water and our lungs are about 90% water. Actually, 70% of the earth is covered with water. Water is considered the universal solvent. It is the key to life as we know it. Let's look at a solution. A homogeneous mixture of two or more substances where the solvent is the material present in the largest amount and the solute is all the other materials present. If you look at the diagram in the bottom right-hand corner, you'll see we're adding table sugar to water. Think of making Kool-Aid. In this situation, the water is the solvent because it does the dissolving. Okay, they both have a V in it. And the solute is the solid that we are trying to dilute or to turn into liquid. So we're going to go in and we're going to look at exactly what is going on inside that water to make it a solution. Here are a couple different types of solutions. We can have liquid solid, such as the sugar that was dissolved in water. You can have liquid, which would be a vinegar added to water. Or solid, which an example would be this metal alloy here of silver and copper. This is actually sterling silver. It's a solid solution. The copper atoms are evenly distributed among those silver atoms. An aqueous solution can be where water is the solvent, which is the most common type of solution. Aqua is Latin for water, so this would be an aqueous solution, as you can see here. Let's take a minute to classify the following as a solution or a heterogeneous mixture. A hot cup of instant coffee, chicken vegetable soup, unfiltered blood, and a chromium-plated steel bumper. Well, the hot cup of coffee is a solution. It is the coffee in the water. The chicken vegetable soup is heterogeneous. The unfiltered blood has many different components. That's heterogeneous. And the chromium-plated steel bumper is heterogeneous as well because there's different metals. So why is water considered the universal solvent? Well, we're going to look at the bent shape of the molecule that you can see here. There's a large electronegativity difference between the oxygen and the hydrogen. We have partial positive charges with the hydrogens and a partial negative charge with the oxygen. We also have hydrogen bonding present. This leads to very strong dipolar attractions called hydrogen bonds. Next, we'll look at the dissolution of an ionic salt. Think of things like sodium chloride, the table salt that you use. And when you add it to water, the salt doesn't sink to the bottom, may initially, but as we stir it, it will then become a solution. So here's what water allows for. It allows for the solute separation, which frees ions from the crystal lattice of the solute. Think of all those sodium and chloride atoms stuck together in that lattice. Then we have solvent separation, which is the breaking apart of the water molecules, and solvation, which is the movement of the ions into spaces in the solvent. All of this occurs at once as the salt dissolves. So here's the solute separation step. We're going to free the ions from the crystal lattice. So energy must be supplied to break the ionic bonds holding the ions in the lattice. Here's the block I was talking about with the sodium and the chloride atoms all stuck together. Add it to the water. Then we need to make room for the solvents and the ions with the solvent separation step. Energy must be supplied to overcome the attractive interactions between those solvent molecules. In this solvation step, we can see the formation of attractive forces between solvent particles and solute particles. With hydration, the surrounding of the solute ions by solvent molecules, and the solvation is when the water is the solvent. A solute will dissolve when the energy released during solvation is larger than the energy needed in the first two steps. We have the sodium chloride crystal where the ions are in ordered lattice. And then we have the dissolved sodium chloride, as you can see with the sodium chloride ions in solutions floating about. So if we consider the ionic compound in magnesium chloride, do you think the hydration energy for this compound is greater than, less than, or about the same as sodium chloride? Since magnesium chloride has the magnesium with a 2+ charge and sodium with a 1+, or the sodium would have a 1+ charge, the hydration energy released for magnesium chloride would be larger because of the charge difference. Our next definition is solubility. This is the amount of solute that can be dissolved per amount of solvent. This can be affected by things like temperature, the identity of the solute, and pressure. Here are some temperature effects. Here's the solubility of sucrose in water, so essentially making simple syrup, if you've ever done this before. It's where you want to take sugar, add it to water, and get it to dissolve. The solubility of sucrose in ice water is 179.2. Picture yourself adding some sugar to a beaker of ice water and stirring and stirring and stirring and stirring. It takes a long time. Sometimes it's frustrating when you're trying to make Kool-Aid that you added the ice and the water and the Kool-Aid and you're mixing and mixing and mixing and mixing. It takes forever. On the other hand, if you bring it to boiling, which is 100 degrees Celsius, you'll see the solubility goes up, so it will almost dissolve instantly for you. We can determine the identity of some solutes based on their solubility. You can see here there's quite a wide range of solubility based on temperature. We have some of our solid salts over here that obviously have a lot higher temperature that they like to dissolve at, where we have glucose and some larger molecules over here to the left. Pressure can also have an effect on solubility. As we add pressure, it can become more soluble. Next, we're going to look at different types of concentrations. Molarity is the number of moles solute per liter of solution. So moles of solute per liter, is the definition of molarity. As you can see, we have varying concentrations in these volumetric flasks here. The first one on the left is a 0.5 molar solution. This contains a 0.5 mole of sodium chloride in a liter. The next one is 1 molar, contains 1 mole. A 2 molar contains 2 moles. So as you can imagine, as we go up, it becomes more and more concentrated. If we are making something like Kool-Aid, it would become a stronger and stronger tasting Kool-Aid. In this case, as the molarity goes up, it's becoming saltier and saltier because it is sodium chloride. We're going to look at some formulas for calculating molarity. Okay? I have my favorites down below. Your book will mention just one that you can use to fill things in. I have these 5 favorites that we will also use as we move through to Chemistry 1 and Chemistry 2. So the first one is the most common. Molarity equals grams divided by liters times 1 mole over gram molecular weight. This is always mole. Gram molecular weight is the molar mass, okay? The number that's underneath the element itself. Always make sure you use liters. Sometimes I'll give you milliliters. You're going to have to convert it to liters. Another one is moles. Molarity equals moles over liters. Okay, if you're given the moles, you can use that shortcut. Liter equals moles over molarity. Moles equals molarity times liters, and grams equals molarity times gram molecular weight times liters. I recommend that you memorize these and write them down before you take a quiz or test because it's an easy reference. So let's try one. How many moles of sodium chloride are there in 200 mils of a 1 molar sodium chloride solution? How many grams? Okay. With this one, it figured out that there's 0.2 molar and 11.7 grams. Now you can use all of the conversion factors if you like. It'll work just as well. We've used those in the past in this course. But if you measure my 5 easy tips, you can just use the calculations that I gave you. Molarity equals mass, or molarity times volume. So 1 times 0.2 is 0.2. grams equals gram molecular weight times liters times mass. Well, the gram molecular weight is 58.443. Okay, you get that by adding sodium chloride together in the periodic table. And the molarity was given to you, and that would equal 11.7. Now let's find the molarity of 30 grams of potassium chloride that is dissolved in 400 mils of water. I want you to pause here and remember, in order to figure this out using one of my 5 problems, you have to figure out the gram molecular weight of potassium chloride. Pause here and hit play when you're ready to see the answer. All right, the first thing we need to do is find the gram molecular weight of potassium chloride, which gives us 74.6. We need to figure out which formula we want to use, which the molarity equals grams over liters times 1 over gram molecular weight. We plug in the information, and we have molarity equals 30 grams over 0.4 liters. Remember, we have to convert the 400 mils to liters. We cannot keep it as mils. Times 1 over the gram molecular weight of 74.6. This gives us a molarity of 1.0. So how do we prepare that solution with this type of information? Well, first we need to calculate the amount of solute that's needed. Okay, so how many grams, for example? We add the solute to the flask and then dilute to the desired volume. Here we'd measure out the correct amount of solid sodium chloride, add it to the volumetric flask, and bring to the level that's needed for volume. Let's do another one. How would you prepare 500 mils of a 0.15 molar sodium chloride solution? Go ahead and pause here and see if you can use one of the 5 molarity calculations that I gave you to figure it out. All right. So this one is using the process of canceling out here. But you would transfer 4.4 grams of sodium chloride to a flask and add enough water to make 500 mils of solution. So grams equals molarity times gram molecular weight times liters would be a faster way to do it. So when we prepare a solution by dilution, we use the dilution equation to find the volume of stock solution needed. Then we dilute to the desired final volume. So let's say we're trying to make a solution because we only have one concentration available. So if we're just sitting with 18 molar hydrochloric acid, but we really need 100 mils of a 10 molar hydrochloric acid, we don't have to go to the store and buy 10 molar hydrochloric acid. We can use our 18 molar and dilute it down to 10. That's very dangerous, and I recommend that you have proper equipment to do that. So this is what I call C1V1 equals C2V2. Some people in your book will refer to it as M1V1 equals M2V2. Same scenario. So let's try an example. What volume of 50 molar sodium chloride stock solution is needed to form 500 mils of a 0.15 molar sodium chloride solution? One of the ways that I have my students recognize these problems is sometimes it uses the words, here's what you have and here's what you need. Or there's 3 pieces of information and you're looking for that 4th piece of information. In this case, C1V1 equals C2V2. So here's what we do. I've got a 50 molar, okay? This is what we need. And we don't know how much, okay? That's what the X is. So C1V1 equals 0.15, which is what we need, and we need 500 mils of it. So if we figure this out algebraically, okay, 50x equals 75, because if you multiply these together, you get 75. You multiply these, you get 50x. Divide both sides by 50 to solve for x, and you get 1.5. What this means is that you take 1.5 mils of your 0.5 molar, add it to a container, and fill the container to 500 mils. You will then have 500 mils of a 0.15 molar sodium chloride solution. So what you have on one side and what you need on the other. Remember that dilution changes the volume, not the number of moles of solute present. So here's a stock solution before dilution. You add water, and after the dilution, the 2 beakers contain the same number of moles per solute, or moles of solute. So here are some steps to preparing a solution. Next, we're going to try doing percent composition. This is really easy because usually you don't need the gram molecular weight. It's just a percent. We have 3 main types of percent composition: mass, volume, and mass per volume. So when we look at the percent composition by mass, we take the grams of solute divided by the grams of solution times 100. Volume is the volume of solute divided by the volume of solution times 100. And mass per volume is grams over volume times 100. So we're going to try one of each of these. The first one is, what is the weight per weight concentration of a solution containing 10 grams of sucrose and enough water to make a total of 100 grams of solution? The reason this is called a weight per weight is because we've got grams and grams, weighing and weighing. Okay, those are always weights. So what we would do is we'd put in 10 grams of sucrose initially. Then we'd add water until the solution mass is 10 grams. This is 10%. 100 grams divided by 100 times 100 is 10%. Next, we'll try volume per volume. This is measuring out a liquid, like in a graduated cylinder, in another liquid. Okay? So what is the volume per volume concentration of a solution made from 25 mils of liquid ethanol and enough water to make 10 mils of solution? Well, in this case, we're going to add 25 mils of ethanol to our graduated cylinder, or sorry, this is a volumetric flask, and we're going to add water until it's filled to the 100 mil line. Since we have 25 mils of ethanol over 100 total mils of solution, because the total volume is 100 mils, times 100 is 25% volume. Next, we have some normal boiling points, or boiling and freezing points. We're gonna look at the colligative properties of solutions. So the normal boiling point is the temperature at which a liquid boils at 1 atmosphere. Normal freezing point is the temperature at which liquid freezes at 1 atmosphere. We can look at the heating curve of water, and I'm sure this will make sense to some of you. Picture yourself putting a bunch of ice cubes in a pan on the stove. The temperature rises as the ice warms from minus 20 degrees to 0, and it's going to stay there until all of the ice is melted. Once all the ice melts and it's liquid, the water is going to slowly start to change from 0 to 100 degrees Celsius. Once the water hits 100, it's going to stay at 100 till all the water is gone and the vapor is converted to water vapor. We also have dynamic equilibrium. This is a situation in which the rate of a forward reaction is equal to the rate of a reverse reaction. We can look at vapor pressure as the pressure exerted by the gas molecules of a liquid. Here's the vapor pressure of water at various temperatures. As the temperature is 0, we've got a very small vapor pressure. Once we reach boiling, that vapor pressure goes up to 906.1 millimeters of mercury. So what is a colligative property? This is a property that depends on the number of solute particles in solution. It does not depend on the type of solute particle, only the number of solute particles. Melting point and freezing point shifts in a solution compared to those in pure solvent, and are examples of the colligative properties. So we have an example here. We add sodium chloride salt to pure water to create a solution. As we add heat, the solution does not boil until heated above 100. As we freeze it, the solution does not freeze until chilled below 0 degrees Celsius. So as you can see, adding the salt did change the heating and boiling point, or sorry, chilling and boiling point. So next we're going to look at getting unlikes to dissolve, such as soaps and detergents. Water dissolves polar substances very well, but what about nonpolar substances? We could use a nonpolar liquid, which is dangerous and expensive and are used at dry cleaners. Or we can use soap or detergent, which has a polar and a nonpolar section and exhibits a long nonpolar tail of carbon, hydrogen, and a highly polar head group. I'll show you a picture. So here's our typical soap molecule. Okay, think of what you use when you wash your clothes. There's a nonpolar hydrocarbon tail on the end and the polar head. This has an ion dipole attraction, and the sodium ion balances the negative charge of the head group. Because the two oxygen atoms share the -1 ionic charge, each has a slightly negative charge. Here's going to be our symbol for the soap or detergent molecule. So what does it mean to be hydrophilic or hydrophobic? The hydrophilic end is water-loving. That's the polar portion. The hydrophobic end is water-fearing, that's the nonpolar hydrocarbon end. We also have myceles. These are structure of soap detergent molecules form in the water. It minimizes polar-nonpolar interactions between solvent and solute, and the nonpolar molecules dissolve into